Okay, hello everyone. Now I know I don't see. Okay, now I see people joining. Hello everyone. I'll just wait 1 more minute to wait for everyone to join. Okay, just to keep the time, I will start. So welcome everyone. Yeah, so welcome to this session on the OBPS workshop that it's on recommended practices for skin temperature observations. My name is Lucia Gutierrez Loza, and I'm part of OASIS. I'm part of the steering committee and ECOP, Early Career Ocean Professional, co-lead in some of the work that OASIS is doing. So this session is organized by the best practices part or a group of OASIS. And I can share with you some, if for you, those of you who doesn't know or are not used to, are not aware of what OASIS is and how you can get involved. I have a QR code here in the slide, but I will also add some information on the chat if you want to follow up a bit more. I'm really looking forward to this session. In the past couple of years, we've had some very successful sessions that led to very interesting work. One is on ocean radiation measurements, and the other one on the need of a community of practice for sea interaction observations that I can also add the links for you if you are interested in the chat. I don't want to take too long. Today, we will have 4 speakers. And remember that the idea of today is to have a discussion afterwards. So please don't hesitate to ask questions. You can use the chat. You can use the Q&A tool. And I will be moderating this session, but I hope that people gets really active and I don't have to do a lot, but other than asking your questions in the chat. So we will start our presentation with Andy Jessup. So he will kind of set the scene, and then we will follow with Sandra Castro, Peter Minette, and Jamie Schottler. So I'm really looking forward, and please, Andrew.
Oops. Okay, thank you. Let me just get my screen up here. Okay, I hope that's all working properly. I want to thank the organizers for inviting me to provide an introductory talk to this session that I'm really looking forward to on ocean skin temperature for the best practices workshop. I'd like to suggest 3 timely topics to start our discussion with. One is that the accurate skin temperature measurements are required for climate quality, heat, and gas flux estimates. And Jamie Schottler's talk will touch on some of this, especially the most recent, very recent findings that the skin temperature has an important effect on the CO2 carbon sink. And then the second topic I think that it should be of interest is, the different ways in which we can estimate the skin temperature. Really, there's 2 possibilities: using physics-based models like the core algorithm, or parametrizations based on wind speed only. And the differences between these are of interest in terms of using these for global climate models, and Sandra Castro's talk will touch a little bit on this. And then finally, I'd like to focus on the new opportunities for more widespread measurements. There are 3 new UNOLS vessels that will be starting to be commissioned next year, and each one of these will have a Rosser sensor on there to provide skin temperature as a standard measurement. This is a really unique opportunity for getting some new data for this area. And then also I've been working in the last few years to develop a simplified sensor that's appropriate for USVs and buoys that would provide also more useful data. So the cool skin effect is an effect that occurs at any air-water interface. Shown here, the ocean surface under quiescent conditions, turbulence is suppressed near the boundary layer, and you have a thermal boundary layer where there's a gradient of temperature to support that heat flux primarily by conduction. This can be appealed to a scaling of Fourier's law that led to Saunders' classic formula for the bulk skin temperature difference being proportional to the net heat flux and inversely proportional to the wind forcing through the friction velocity. As the wind speed increases, turbulence becomes important. This thermal boundary layer becomes periodically disrupted and renews, and so that's actually a dynamic process. When we talk about the skin temperature measurement, bulk skin temperature measurements, that's an average measurement that includes this dynamic process driven by wave breaking and large-scale breaking. We can parameterize the bulk skin temperature difference as a function of wind speed, an example shown here with the data, and then a number of curves that over the years that have been shown to describe some of a lot of the data that's been gathered. The differences then between the physical model and the wind speed parameterizations has recently been highlighted by a couple of papers independently looking at the importance of the skin temperature for the CO2 sink. Here is plotted the bulk skin temperature difference versus wind speed. The dashed line is the Donlin wind speed parameterization, and the solid line is the core algorithm, with the shading being 1 standard deviation about that. You can see that there are significant differences at low wind speed and high wind speed. This is for a global data set of several decades that was used to drive the model. And then Bellinger looked at the difference between these two approaches by using a delta T model very similar to the core algorithm, and the difference between that and the wind parameterization. On a global scale, you can see it's quite varied, and also the magnitude approaches the magnitude of the bulk skin temperature difference itself. So this, I think, is a timely topic to investigate because of the importance of driving these global climate models. Now, getting to the actual measurement that's made, how we make that, as I said, I've been working on simplifying the measurements. The conventional approach, which I think we could describe as the current best practices, is to use a single radiometer in the atmospheric window band of 9.6 to 11.5 microns with a mirror that then rotates to look at 2 internal calibration black bodies to calibrate the instrument, and then looks at the sea in the sky, and the sky measurement is necessary in order to correct for the sky radiance. And this has been well documented over the last couple of decades that these instruments have been developed. Over that period of time, the commercially available radiometers have significantly increased in their stability, and to the point where we now can use a single point calibration with an ambient temperature black body, eliminate the mirror, and that allows us to use separate radiometers for the sea and sky, which simplifies the instrumentation. And another development that I think is really promising is to use an optimal band, which is a technique that's used by the MARI, the instrument that Peter Manette uses, where we use a waveband with a large atmospheric optical depth. And this, as I'll show later, reduces the effective emissivity uncertainty, and also provides the possibility of modeling the sky radiance based on temperature and humidity on the ship to forego the sky measurement, or on the platform, I should say, which is appropriate for USV and buoy deployment. So I wanted to contrast the difference between these approaches. The Rosser is an example of a conventional approach, which I'm using as a reference standard for my instrument development. It has a radiometer and a scan drum here with a mirror in it that looks at these 2 internal black bodies and then out at the ocean and the sky. My approach, which is for a sensor I call IRIS, is to use a similar radiometer, but with a simple baffle block on the front here with a flat plate black body that periodically rotates down in front to do a 1-point calibration. And then we have a separate radiometer for the sky measurement that has a rain guard to protect from rain. So looking at now the details of how we actually make these measurements, if you look at the surface with a radiometer, it'll measure some radiance that's is made up primarily of the emission from the skin. The emissivity is 0.97 to 0.99, and then there's a small but significant contribution of the sky reflection. And the magnitude of this sky radiance is going to depend on the waveband that you use. When you're in that atmospheric window here, like the Rosser or the Iris standard band, then you have a wide dynamic range in that radiance from clear sky, very cold, to warm, corresponding to the clouds that are about at the same temperature as the air. So that wide dynamic range of the radiance, sky radiance, can affect the accuracy because of the uncertainty in the emissivity. Whereas the optimal band approach is to use a band that's very close to the edge of the atmospheric window so that the sky effectively looks opaque because the radiance comes just from a few kilometers within the ship. So the radiance is relatively invariant. That reduces uncertainty in the emissivity effects. So what we've done over the last few years, I've deployed the Iris with 2 Rossers in several cruises, and the results shown here are from a cruise in the S-mode first cruise in 2022. I've done scatter plots of the Rossers versus each other, and then the Iris standard band versus the Rosser, and the Iris optimal band versus the Rosser. You can see they all look very similar, and the statistics are summarized here. The mean differences are on the order of a few hundredths of a degree. Standard deviation is about 0.1, which is consistent with what we expect for an accurate measurement. And so we can conclude that the Iris approach, both the standard and the optimal band, provides comparable accuracy to the Rosser. So now to speak a little bit about skin temperature measurements from USVs and potentially buoys. We've looked into this for both on the sail drone and on the Swift buoys. I wanted to focus on the sail drone here today. The sail drone standard configuration has a single down-looking radiometer on it. It does not have a sky measurement radiometer, so you can't correct for the sky reflection under the normal circumstance deployment. And in general, there's no supplemental calibration on these deployments. They're just the radiometer, so you have to rely on the stability and laboratory calibration. In 2019, the sail drone looked into putting both up and down looking radiometers on the sail drones, one in the Gulf of Mexico and then in another incarnation in the Arctic that Peter Manette's talk will address here. And then in the S-mode cruise, I had them add up-looking radiometers to the boom on a couple of the different sail drones. So we have sky-corrected measurements from the sail drone, which I wanted to show an example of here. This is about a 5-hour time series where the sail drone was sailing straight on a line across a strong temperature front, and the ship was tracking it, had to go back and forth here because it couldn't go that slow in a straight line. But in any case here, they're within about a kilometer of each other. You can see that they track each other nicely here. And if you do a scatter plot, the RMS difference is about 1/10 of a diagran. The average is a little bit larger, but this shows really promise, I think, for using these effectively uncalibrated sensors from a USV if you take the care to make sure they're stable. And then the optimal band results should be similar from a USV. Just looking at my time here. The idea, though, is from a USV, it would be better if we didn't have to put an additional sky measurement on there because of a number of things. And so this optimal band gives you this possibility of modeling the sky radiance. So we've looked into that using our S-mode data where there were a lot of radiosondes. And so here are 2 examples of a clear and a cloudy radiosondes taken during S-mode. On the left is the temperature profile, on the right is the water vapor profile. The black trace is the clear sky condition. The blue trace is the cloudy. Here you can see a nice inversion here. We don't need to really model the inversion because you can use the air temperature as an estimate of the cloud temperature because they're so close under these conditions. But to model the radiance of the clear sky, we can fit a line since we're only going up to a few kilometers. The dashed line here is the fit to these individual black traces, the clear sky conditions. And then the red is the average slope for the entire cruise. It's So you can take these types of profiles and put them into a software like Modtran, which will provide you the downwelling spectra of the sky radiance. And then if we multiply that by our spectral response shown here in red, we can get an estimate of the sky radiance. And then that can be converted into a sky temperature for comparison to the measurements. And that's shown here. I have a time series of air temperature and the measured sky temperature in green for the entire cruise. And when it's cloudy, they are very close. When it's clear, there's some deviation, although rather relatively small. These symbols here are the results of the Modtran sky, T-sky for the 3 different cases using the radiosound profile itself, a linear fit to the profile, and a constant lapse rate and water vapor profile slope from the entire experiment. You can see they all pretty much fall on top of each other. And that's summarized. The result then is summarized here when we plot the skin temperature using the Modtran sky temperature versus the skin temperature using the measured. With these 3 different symbols for the 3 different approaches, they all fall on top of each other, and the differences are just a few hundredths of a degree. So this provides me some hope or optimism that we can forego the sky measurement on USEs and buoys to get an accurate measurement. And then finally, I want to highlight this really exciting opportunity for long-term continuous measurements from the 3 UNOS vessels that are called the regional class research vessels. They will be commissioned starting next year. It's an excellent opportunity for getting a large data set over a wide range of conditions. And then we'll have this skin temperature measurement on a research vessel where other people can propose to add additional measurements, for instance, flux systems for doing covariance measurements along with the skin temperature measurements. There's a need for quality control of this data because when the ship's not moving, you have wake interference. So I'm going to be involved in the commissioning, and then I'm proposing to NSF to set up a support group to provide quality data so that we can be used by the community. And I'm really interested to get feedback from people about how important they think these measurements are and how you would use this for your research, since that would be helpful in getting the funds to provide the support. So that's pretty much what I wanted to cover here as to start this off. I'll just conclude with the highlighting the discussions topics I suggested, and I'm happy to take any questions if there's time before the next talk.
Yes, I think we have time for 1 or 2 questions if people has something that want to comment on or ask Andy about. You can use the Q&A or, yeah, I think for now. Okay, there is 1 hand. Let me see. Yes. Megan, now you should be able to speak.
Hi, excellent, wonderful introduction. When you showed that sail drone in a comparison with the S mode, was that you had 2 different skin temperatures? Was that with the gray setup that you have down on the hull, or using the standard locating sensor, but with for downward?
Right. Okay. So yeah, on the S mode cruise, there was just the radiometer on the boom and then the sky radiometer that was added. So this configuration on the bow was not available on the S mode cruise. So this is just the boom measurement. Yeah. So that's, I think, shows really good promise for if we can basically we would need to retrofit the sail drones with the optimal band radiometers, and then I think we could get a good skin temperature measurement
going into the future.
Going into the future, yeah.
Okay, great. Thanks.
You're welcome.
Great, thank you. I think we will move on to Sandra's presentation, and but please, if you have more questions, just save them for later. I see that there are a couple of questions on the Q&A, so we can take that afterwards in the discussion, if that's
Great.
okay.
Okay, I'll stop sharing my screen.
Yes, thank you.
Okay. We can't hear you.
Sorry about that. Okay, so I'm Sandra Castro, and we just hear Andy Jessup talking about the skin SST and how we can use the winds to estimate the cool skin effect. And in this presentation, I'm going to show you some new data sets that question the validity of that assumption, meaning that the wind speed is enough to characterize delta T. So hold on. I am not able to move. Okay, now. So thanks to Andy, I don't have to spend a lot of time in this plot. So you guys now understand what the cool skin is, so what delta T, what the skin is. So just a little reminder, every time we have a net heat flux from the ocean to the atmosphere, we get a cooling at the surface of the ocean across a very thin layer where the molecular processes dominate. So this is what it's called, the cool skin. And what we're interested is in determining what's the temperature difference across the cool skin. So it is a gradient, as you can see, but we usually use the simplification of the temperature at the skin minus the temperature at the base of the cool skin or the south skin. So previous theoretical work on delta T showed that delta T is directly proportional to the heat flux and inversely proportional to the wind stress or friction velocity. But due to the fact that we don't have really good heat fluxes, we were forced to overlook these heat flux dependence. And delta T is usually characterized as a function of the wind speed only. So I'm going to take a new look at these simplified models that consider that the wind speed is only a function of, the delta T is only a function of the wind speed. So these simplified models started with Donlan and co-authors back in 1999. And these plots show the concept here. And basically what they did is they did scatter plots of delta T versus wind speed. In this case, the skin SST was from infrared radiometers. So even though there's a lot of scatter, we can see that most of the points follow this curve, which is a negative exponential. So here's the original fit from Donlan. And then this sort of experiment has been repeated many times for different parts of the ocean. And as we can see on the right, the result is always the same. It's essentially the same negative exponential with slightly different coefficients, except perhaps for that last curve in there. There is pretty good agreement between among all the models. So Donlan also observed that for wind speeds greater than 6 meters per second, delta T approached a constant asymptote. So he proposed general validation technique using buoy temperatures to validate satellite skin SSTs and using these asymptotes. So he just proposed that you need to filter wind speeds for to filter the data for the buoy data for winds greater than 6 meters per second. We add a cool bias, which is the constant term here in the negative exponential, and then you can transform buoy SSTs to skin SSTs. So this is the common approach and it's still done to this day. So I mentioned 3 different data sets that sort of questions the simplified wind speed models. 2 are from cruise data. These were provided by Andy Jessup. They use different infrared radiometers, the Rosser he mentioned, and serums, which is a previous incarnation of the radiometers. And for the depth temperatures, we used a trailing thermistor named called the Snake, which measures SSTs at a depth of 5 centimeters. For the third data set, it's a different data set. We use skin SSTs and buoy temperatures. For delta T, the skins are from the SLSTR on Sentinel-3 satellites, and the buoys are the trusted buoys, which are special buoys designed to validate SLSTR, but they're unique in the sense that they are their measurements is SI traceable, so they're calibrated. They measure temperatures at 17 centimeters below the surface. And for the winds and fluxes, in this case, we consider ERA 5 reanalysis. So as we can see here in the map, I selected buoys from 2019 to 2022 for latitudes about 40 degrees north, so they're high latitude comparison. So let's start with S mode. So this is a NASA ongoing experiment, and the data here comes from phase 1, which took place in 2022 off of San Francisco Bay. And the objective was to sample these strong front continuously. The front persisted for about 3 weeks. So here we have on the skin SST measurements across the front, and we see strong variations in SST as the front is crossed. The magnitude of this front was about 4 degrees Celsius. If we look at 2 of these crossings in more detail, we have here from the wind vectors that the wind was pretty constant for this day. And here on top, we have the time series for the skin, the snake, and the air temperature. So we can see there was a change in stability across the front. But what is important here is that the warm side of the front, where the conditions are unstable, we have a separation between the skin and the snake. This indicates the presence of a cool skin. And in fact, we can see in the bottom that the cool skin grew from 0 at the cold side of the front to about 0.2, 0.3 degrees Celsius at the warm side. For other crossings, on the right, we have the delta T and heat flux modulation with the skin SST. And we can see that there is a strong correlation between the delta T modulation and the heat flux modulation. So finally, this is the scatter plot. So delta T versus wind speed, color-coded by heat flux. The red curve is the simplified Donlon model. And what's interesting for the S mode is that most of the points do not align with the Donlon curve for a great portion of the wind speeds. So we can see from the colors that these conditions corresponded to very low heat fluxes. In fact, we have 0 delta T for 0 flux. Only when the wind speed and the heat flux increase past a certain threshold does the observations converge with the Donlon model. This is a second experiment, and I don't have time to describe it in detail, so I'm going to jump to the delta T versus wind speed dependent. And here, the interesting part is that we have an observed dependence that has the same shape as Donlon, but the curve is pushed down to stronger, cooler delta T's. So this is interesting because it's a similar plot to the one Andy showed for the equinox data set, where there was one curve that it wasn't part of the Donlon family, but here we have the exact same dependence with EPIC. These are the SST from satellites minus the SST from the buoy for the high latitudes. And yes, we have a lot of scatter because this is an indirect measurement of delta T, and the fluxes from air are pretty coarse and the wind speeds. But the advantage is that we have a lot of matchups, so we can sort of trust the mean dependence. And in any way, the mean dependence show really good agreement with the simplified models for the low wind speeds, but shows a tendency to depart from the Donlon curve for the high winds. So putting all the three together, we have 3 types of departure from the Donlon curve that we have identified in these examples. We have cases where there's no dependence between delta T and the wind speed. We have cases where the dependence has the same shape as Donlon, but is pushed downward to cooler delta T's. And we have cases where the observations follow the dependence to a point, but then for higher winds, we see some departures. So what happens if we bring in the heat flux? So these are scatter plots of delta T versus heat flux. And we can see for S mode and for the trusted buoys that we have evident dependence of the heat of the delta T on heat flux with increasing delta T's for increasing heat fluxes. So this is no surprise. This is just corroborating the theory. What's surprising here is that EPIC didn't show that kind of dependence. So we wanted to quantify the impact of the heat flux of the simplified models. So we did this little experiment where we stratified the data by heat flux ranges, and something very interesting happened, and it's pretty clear here for the trusted buoys. So we can see that the individual dependencies for the separate heat flux ranges sort of follow Donlon or the simplified models pretty much. But as the heat flux increases, the curve is pushed down. As the heat flux decreases, the curve is pushed up above Donlon. So the final question here is, can we improve our estimate of delta T by explicitly including the heat flux effect? So these are scatter plots of the error in the prediction using the Donlon model. So this is the observed delta T minus delta T from Donlon versus heat flux. And yes, we see a linear dependence between the error and the estimate and the heat flux. But what's important here is I want to guide your attention to the individual values. And what this is saying is that if we want to improve the delta T prediction accuracy by 1/10 of a degree over simplified prediction, we would need to know the heat fluxes to an accuracy of about 150 watts per meter squared. So given the current reanalysis products, I think we are there. We can provide such accuracy in heat fluxes. So our argument is, yes, we can now improve delta T predictions by explicitly including the heat flux in a parametrization of delta T. And the reanalysis might be the solution. So in conclusion, the main take-home points are that delta T, simplified delta T parametrizations are pretty useful in the absence of reliable heat fluxes, but let's not forget that DT depends on heat flux. And these heat flux dependence, we show that there are conditions in regions where this dependence might be affecting the simplified model by pushing it up or down depending on the heat flux variations. And we can see that with these new conditions, variations from Donlon are up to 4/10 of a degree, and we suggest that we can improve the accuracy of delta T estimates by explicitly including heat fluxes if we know them to 150 watt per meter square accuracy, which the reanalysis might be of sufficient accuracy to do this. So that's my presentation.
Thank you, Sandra. I think we have time for only one quick question now. If anyone has a very pressing issue to ask Sandra, otherwise, yeah, there is, okay, the hand disappeared. But yeah, I would suggest that we move on instead, and then we can ask all the speakers at the end and have a nice discussion afterwards, if that's okay, to keep the time. So thank you again, Sandra. And so now it would be time for Peter. Welcome.
Well, hello. I'm Peter Minette, and I'm at the Rosenstiel School at the University of Miami. What I'm about to present is actually the work of Chong Jia, who is online here, and it forms part of his PhD work. And the title shows that we're going to talk about deriving skin SST from radiometers on sail drones. So these are two spectra not taken from sail drone data, but taken from the Marine Atmospheric Emitted Radiance Interferometer, which is the instrument we use to derive skin temperature on ships or from ships. And the bottom set of curves they're plotted as a function of wave number, which is what people in this field usually use rather than wavelength, but it's a reciprocal wavelength. It's the number of waves of infrared radiation in 1 centimeter. So 1,000 wave numbers is 10 micron wavelength. The bottom set of lines is pointing at the sea at different angles for each color. And if the sea had an emissivity of 1 and a reflectivity of 0, what we would see would be straight lines on top of each other representing temperature derived from Planck's function, from the radiance measurements. But we don't see that. And what we see is a very strong dependence on the angle of the measurement, showing lines, which are reflected emission lines from the atmosphere that Andy mentioned in the introduction. And those are shown in the top panel. So the general approach is that it is necessary to take a sky measurement at the same angle as a sea measurement in order to correct for this. And so this is how we do it. It's either with 2 radiometers or a single radiometer with a scan mirror. The sea view is not just the emission from the surface, but it also includes emission from the atmospheric layer between the instrument and the surface, and a reflected component of the sky radiance reflected at the sea surface. So to derive the skin SST from the radiance measurement looking at the sea, we have to remove the effects of the atmosphere between the instrument and the sea surface and reflected sky radiance. For radiometers mounted close to the sea surface, such as on sail drones, these terms, related to the atmosphere between the instrument and the surface, can be neglected. The path length is less than a meter. We need accurate measurements or estimates of the reflectivity, which is 1 minus emissivity. So, Andy has already shown the sail drones. These are the 2 that went into the Arctic in 2019. This is as they were deployed in Dutch Harbor in Alaska. And they're 7 meters long, and the mast is 4.5 meters above the waterline, and beneath the hull is a keel which extends to about 2 meters depth. So in 2019, we deployed 2 of these for 150-day cruises in the Pacific sector of the Arctic Ocean. And each carried a pair of Hytronics radiometers for the derivation of skin SST. These are the tracks of the 2 sail drones in the 2 different colors, starting and ending at Dutch Harbor. And these show what we call the unicorn configuration of the radiometers. Oh, I'm trying to get a point in, never mind. Okay. You cannot use all the measurements. You have to discard a very large fraction. But when you have done that, the RMS uncertainty is about 0.12 K, which I found remarkable. And even though Sandra is correct that the wind speed dependence doesn't have all of the information that you really need to predict the skin temperature, what we show here is that the black line agrees very well with many of the other independent data sets derived from ship-mounted radiometers. And the wind speed from the wind speed dependence from the sail drones is in family. And if you look at the high wind speed intercept, all of the parameterizations derived from different data sets, including the sail drones, are within 20 millikelvin. And that is, again, truly remarkable. And that's written up in this paper by Chong. One of the big issues with doing radiometry from sail drones is the stability of the vehicle. And Chong used radiative transfer modeling to determine the acceptable range of pitch and roll angles for a good retrieval of skin radiometer, skin temperature from the radiometers, and that is only within that shaded area here. All other data have to be discarded because the sky reflection measurement is not appropriate for the correction of the sky emission reflected at the surface before it gets into the sea viewing radiometer. There are other challenges, of course, in the Arctic especially. This picture on the right is taken from one of the cameras on the masthead of the sail drones, and these are very useful because they can determine what conditions, in which conditions the measurements were made. Here, sail drone 1036 is nudging up against some ice. Wasn't intended to, but it does happen many times, in fact. So you're not really quite sure what you're measuring from the sea viewing radiometer. But from the point of view of comparing with satellite measurements, it doesn't matter because this was a very cloudy day. So the calibration stability of the Hydronics radiometers, which at the outset I thought was going to be a real limiting factor, is now very good over periods of several months in the field, which is a big request of these instruments. I used to use Hydronics radiometers 25 years ago and was not impressed with what we could do at sea at that time, but Hydronics have made tremendous improvements in the stability and the calibration accuracy of their instruments. So relying on the manufacturer's calibration information is good enough to get skin temperatures to about 0.12 degrees. And the simple protection of the Skyview radiometer using a sighting tube to try to keep the spray and the rain and the snow out appears effective with drainage if any water gets into the tube. For future deployments in this configuration, if there are any, it would be really useful if the same types of radiometers were used for the sea view and the sky view. For reasons which I think are related to cost, and the cost difference isn't all that tremendous, is that the sky view, because it doesn't need to be made with such accuracy, could use a cheaper radiometer. The unfortunate consequence is that the spectral response function shown in blue of the sky viewing radiometers doesn't match that of the sea viewing radiometers. The peak of the sky viewing response is at about 9 microns wavelength, whereas at the sea viewing radiometer, it's at about 12 microns wavelength, and that is important. It has to be corrected for. Similarly, the sea viewing radiometers, 3 of the 4 that we used seem to have come from the same batch. And they had very, very similar spectral response functions. In fact, you cannot distinguish them. They're all under the purple curve. The 4th is from presumably a different batch, and there is a slight difference, and that has to be corrected for. Saildrone accepted the manufacturer's calibration, and against my better judgment, that turned out to be good. But I think in future we could improve the accuracy if we had proper pre- and post-deployment calibration against SI traceable laboratory calibration targets. And for applications in polar regions, the issue of getting too close to ice is a problem. If the sail drone gets trapped in the ice, we just have to wait for favorable conditions for the ice to open up a bit and the wind to drive the sail drone out of those conditions. We have no mechanical propulsion. It's just on the wind. So I tried to get SAR, synthetic aperture radar imagery of the operational area, but that was not feasible. you need to request the SAR to be switched on the various satellites on which the instruments fly well ahead so that that can be planned. Well, we don't know where the ice is going to be well ahead, and we don't know where the sail drones are going to be well ahead. But I think there is some possibility of trying to coordinate better with the operators of satellites that carry SARs, and those are mainly European Sentinel-1A, B, C, and D, and Canada RadarSat. And there are others as well. So summary. After very careful quality assurance, the skin SST from the radiometers in the Unicorn configuration on the foredecks of the sail drones can provide skin SST data with sufficient accuracy for scientific research. The high latitude deployments of sail drone provide data from a very, very sparsely sampled area, and yet it is critical to determine the consequences of climate change through this feature of Arctic amplification. And yet we have very little data in the Arctic for that. And the sail drone skin SSTs that we have derived are being used to assess the accuracy of satellite-derived skin SSTs in the Arctic, provide information on atmospheric correction algorithms to do that in the Arctic. Oops. Study the thermal properties of the Arctic sea surface, including cool and remarkably warm skin layers and diurnal heating. And the data are available. They are already being used by NASA, and they're available for FELIX, which is the European data set for comparing satellite measurements with shipboard and now sail drone radiometers for the accuracy assessment of SST skin derived from the European satellites and from others. Yeah. Sail drone-derived data are openly available at the University of Miami Library's scholarly repository, and the total sail drone data from the Arctic are available from the PODAC. And I would like to acknowledge funding from NASA and support from sail drone. Those are the references of papers that have come out of the 2019 sail drone deployment, with Chong Jia as lead author. And I would just like to end by quoting a Nobel laureate summary about the problems we face. God made the bulk. Surfaces were invented by the devil. And that was Wolfgang Pauli, who was a Nobel laureate in physics in 1945, and he got it right. Thank you very much.
Thank you, Peter. I was wondering if you could maybe those links that you mentioned about the data, if you could add them in the chat as well. So
okay, I can do that.
Yes, great, thank you. Is there a question for Peter? I see one from Johan Edholm in the chat. So I'll just very quickly read it. So Johan is asking whether so for USBs, and I would argue that not only USBs, but many different type of platforms, there is no space or enough power to house infrared sensors, and instead the SST is measured at different several centimeters or even deep meters depth. And so he's asking, is there a way that we could convert this SST to skin equivalent, or at least to take steps to minimize the bias and uncertainty when estimating turbulent heat fluxes? The observations could vary from 1 Hertz to a 30-second average every 10 to 15 minutes.
Mm-hmm. Well, first of all, the comment about the power requirement is dead right. And the sail drones are reliant on solar power generation during sunlit hours and batteries when there is no sunshine. And the 2 radiometers on the Unicorn were one of the major power drains on the vehicles. I think you should direct your question about how you can get skin SST from subsurface buoy temperatures to Sandra, as she has looked into it. When we started out this, Craig and I gathered a lot of data from a number of investigators using different types of radiometers on many ships and put the data set together. And to our surprise, we got very consistent data. And as Sandra said, at that time, there were not really good estimates of heat fluxes, but we found that there was a useful parameterization in terms of wind speed, which is measured from ships. There is an issue of flow distortion around a ship, but I've looked at that with some New Zealand colleagues, and that is tractable. Anyway, Sandra is showing we need better estimates of heat flux, and they may be coming available. They may be available now. I'm a bit concerned about the spatial resolution of the reanalysis data, such as ERA5 and MERA2, but there is definitely a way forward there.
Okay, well, we can continue with this discussion afterwards. So we have the last presentation from Jamie. So please go ahead.
Thanks, Lucia. So following on for Peter, I'm going to be talking about a little bit more about skin temperature, but particularly why it's actually incredibly useful and important for guiding international policy, focusing on global carbon assessments. So it was back in the 1800s that Eunice Foote was actually the first person to experimentally show the properties of greenhouse gases and the fact that these gases could absorb energy but also re-radiate them back out. And then since then, our knowledge of how those, particularly carbon, how it moves and evolves in the atmosphere, but in the ocean as well, as it is evolved immensely. And you can see the importance of the oceans within this global carbon budget and assessments and cycles if you compare Venus, which we have here on the left, with the Earth. So they're actually, Venus is our closest neighbor. Earth and Venus are about the same size, about the same distance from the sun. We receive about the same amount of energy from the sun. And so that the two planets have evolved in very similar ways. And they both have about the same amount of total carbon within their systems. But the difference with Venus is that it's all airborne. And so the temperature at the surface is about 470 Kelvin, and the atmosphere is, to us at least, very highly toxic because it's full of carbon dioxide. In contrast, we have a lot of water on Earth, and the oceans are, in fact, the second largest long-term store of carbon on Earth, second only to the core of the Earth itself. So clearly the water component is incredibly important, both in the carbon cycle, but also in terms of carbon assessments. And every year, these global carbon budgets are collated. It's a huge international effort, and they're used to advise governments to motivate reductions in emissions, or at least that's their aim. And sometimes that's successful, but that's what they're designed for use. They're also increasingly, these carbon assessments, particularly for the oceans, are being used for studying food security and conservation as well. So, identifying regions and ecosystems at risk from long-term acidification or even short-term acidification events. So clearly the oceans are a fundamental component of these assessments, but they're actually a really powerful constraint on the whole budget itself, the whole global carbon budget. And you can see that if you look at how they're actually constructed. So first of all, that for these carbon budgets, they take the atmospheric observations as one of the sources, one of the sinks, and then combined with that, we take the emissions from fossil fuel usage, which are relatively well known and quantified, and these are combined with our land use change, which are relatively poor estimates, but they're much smaller components, and this gives us our total source, what's going into the atmosphere. And then we take observations of the amount of carbon that's going into the ocean, and there's a combined observation and model approach for that. And that collectively allows us to model the vegetation component. And the reason the vegetation component is only modeled is because it can't be easily observed directly because it's so heterogeneous across the land. And then along with that, we also have the relatively poor estimates of the land to ocean carbon flow. And collectively, that makes up the complete carbon budget, but you can see the only two observational constraints in that whole budget are the atmosphere and the ocean components. So knowing our ocean component well allows us to find out more and determine more about the other weaker components of the budget. And this is beginning to be shown. We had work led by Andy Watson back in 2020, where they actually took two independent estimates of ocean carbon data, and they used that to constrain the land-to-ocean carbon sink. That wasn't the main focus of the work, but that was one of the components that came out of it. And then more recently, Nicholas Mayo, this year, in fact, used ocean carbon estimates to constrain the decadal trend in the land carbon sink. So it's clear that both the ocean data is critical for the budget itself, but also a really powerful constraint on the global budget. And one issue that's now being grappled with by the ocean carbon community is how should those measurements be taken, and how should we actually produce a very good representation of the exchange itself versus what we can currently do in terms of our measurement capability. So this is a cartoon of the interface between the atmosphere and the ocean. The solid blue line is our interface. And essentially, if you want to calculate the exchange of the gas, you need to look at the concentration above and below a really thin layer at the very surface, this mass boundary layer. But in reality, the measurements are typically taken about 10 meters above and 5 meters below, so some distance away from that interface, and that's a practical aspect. But also this measurement height and measurement depth can be variable. It's not constant. So clearly there's this issue of you're taking measurements either side of the boundary, but it's not really at the point where you're trying to understand the measurement. And as we've heard already, infrared measurement depths are much more better aligned with the actual interface that we're interested in. And because the concentration of the gas, carbon dioxide, is highly temperature sensitive, it raises this question and highlights the point that infrared measurements may well be a much more appropriate way of calculating your concentration, because it means you can take into account the temperature change across that really thin layer. And this is work that has been focused on quite a lot in recent years. There's 3 different publications here that are quantifying this. And within this, we have different components or different issues that have to be dealt with. There's the issue of the cool skin effect, which actually over large areas increases the amount of carbon that goes into the water. There's also the issue of warm layers, which can have an opposing effect. And there's the issue of artificial warming of measurements. So this is where measurements are taken at depth, say at 5 meters, and this measurement is warmed through the ship before it's actually measured. And so that has an additional impact. And if you don't account for all of these, you can end up with very confused estimates of the ocean carbon sink. And so these 3 studies that have been more recently published, they look at it from a theoretical and observation-based and modeling approaches, and their results are consistent with each other. So clearly the ocean is really important for these carbon budgets and for the global carbon assessment itself. There's this need to address kind of more precise and accurate measurements. And if you have disagreement in terms of your methods and your approaches, one way to actually address that is actually have a reference measurement of which you can assess all of your different data sets against, an independent reference. And so there's this potential for a fiducial carbon dioxide flux reference measurement data set. And this idea of having a reference data set was identified by Rick Wanokoff and authors back in 2019. And they identified this need as a reference measurements for global carbon stocktakes. And as I've just talked about, this issue of different vertical temperature gradients can introduce biases into your calculations. And there's a whole bunch of references here identified why that is an issue. And then we did a kind of forward look, a community review some years ago, and this identified that if you have coincident eddy covariance with sea surface skin data, then it actually allows you to understand, or could allow you to understand more about the air-sea transfer process. And this is also known to be a large source of uncertainty within these ocean sink estimates. And then more recently, Jianzhu Dong, who I think is on the call today, he proposed that if you have a coincident measurements of eddy covariance and also bulk flux measurements of gases, then it allows you to understand and characterize the issues I've talked about in terms of the impact of the skin and warm layers on gas fluxes. And then the same author also more recently highlighted that there's this alarming drop in situ ocean carbon measurements. And so collectively, all of this suggests that there's this strong desire and need for additional CO2 flux reference measurements that include sea surface skin measurements. So then the last point is, the question is, how accurate or precise do these measurements need to be? If we take a climate data record as an example, it's quite easy to show. And so this CCI, the SST climate data record, has a stable cool bias of 0.03 to 0.05 Kelvin. If you know that, if it's well characterized, that can actually be removed from the sea surface temperature data prior to you calculating your gas flux. So as long as you know that, you can remove it. But if you don't know it, it can alter your global net flux by up to 7%. So it's quite a big issue, even though that is a relatively small bias from a sea surface temperature community point of view. It has a relatively large impact on the gas fluxes. Similarly, for T-skin, the precision for CCI dataset is quoted as being about 0.1 Kelvin. And again, if this is known, it could be propagated through the gas flux calculations, and ideally with information on time and space varying uncertainties can also be propagated through, and that is beneficial. So for sea surface skin data to be most useful for CO2 gas flux calculations, we need to have characterized accuracy, particularly for bias, and it needs to be stable. Any bias needs to be stable through time. And we need to understand something about precision. And ideally, you want spatially and time resolved data uncertainties following metrology approaches, such as the generalized measurement uncertainties for measurement protocols and guidance. However, those sea surface skin data are far more powerful for these carbon assessments if they're collected coincident with gas flux data that is well characterized from well characterized systems, both direct and indirect, so that's eddy covariance or bulk methods, but also with meteorological data, because then that allows us to apply, as one of the earlier speakers talks about, there's things like the NOAA approach, the NOAA core approach for actually calculating the skin signal and impact. And that's it. Thanks for listening.
Thank you, Jamie. Questions for Jamie? Yes. Chris, give me 1 second. So, wait. I'm trying to make Chris a panelist. Yeah, now there you are. You should be able to speak. We cannot hear you, Chris. No, I don't think it's working. Maybe you could ask your question in the Q&A. Okay, we can continue with another question while Chris Farrell fixes, I guess, I hope, his microphone. Any other questions for Jamie? Or we could actually we could open the discussion to all the panelists if anyone wants to join the conversation. I see there are a few questions in the Q&A, so we could start with those if that's okay. Yeah, so I guess these questions will be a bit. Sorry. Did you say something, Andy?
Oh, I was going to say I could look at those questions and field a few of them, and then
yes,
if you, as a start, if that would help. So
yes,
Jim Edson asks about using broadband IR measurements to estimate the sky temperature. I think that's a useful approach, especially on some platforms such as the sail drone, where they've tried to make well, in general, I think you could see, even though whether or not if from a ship, I'm sorry, backing up, if from a ship, if you have the long wave measurements, we have done a comparison between the sky measurements and the long wave measurements, and there's a very strong correlation. And so I think you can estimate that. But it also is going to depend on the angle of your measurement. And so you need to kind of parameterize that space. But I think it is practical in the absence of a sky measurement to be able to use long wave broadband measurements. Chris Farrell asked, what's the time resolution of this T-skin comparison stat? So the measurements that I showed were basically 4-minute averages within a 1-minute calibration. So effectively, they're like sampled every 5 minutes, if that answers your question. And are these published? Well, I have a manuscript that I'll submit by the end of the year. That's my goal. Krista asked if international research was to be available for campaigns mentioned at the end. Yeah, so these new research vessels, it's a standard UNOS vessel. If you do research with NSF or ONR, then you can apply for ship time. And so there's collaborations potential through that. And oftentimes too, if you know, if these ships are on transit legs, then there's empty berths. People can propose to add on if they don't interfere with the ship. So, but I think it's probably through collaboration is the best way for international participants to use the vessels. Yeah,
James Hudson
Chris,
has a raised hand. I don't know if you want to take that.
Sure.
Yeah.
Let's go live. Jim, how are you?
I'm good. This is it's been a great best practices session, I have to say. And so Jamie, you know, obviously a lot of us like this idea of, you know, investigating the cool skin effect on gas exchange, but in order to truly do that, you need to measure the flux directly. We also are probably aware this is not an easy thing to do from ships or buoys. And I'm just wondering, yeah, imagine having a roster on, you know, a fixed platform. And of course, I don't run MVCO anymore, the Air Signal Action Tower. So I'm allowed to toot its horn a little bit, I think. But imagine having a flux package on that, measuring CO2 directly with a roster looking down at the interface, which we've done in the past, and it worked really well. I think those are the sorts of reference stations that we need to identify and start to use again. So that's, and you know, there may be more given how much activity there is with, say, offshore wind. And so just things to think about, that, you know, we need as accurate as possible CO2 flux measurements to really investigate some of these processes. So that's my soapbox.
Yeah, I completely agree. And having a fixed platform and therefore you being able to, you know, collect measurements over a really long period of time is definitely the way forward. I have tried to sort of interact with offshore wind farm companies and groups, and particularly in Europe, they tend to change hands really quickly. So it becomes a really hard thing because as soon as you start working with one, it swaps to a different company.
Yeah,
but I think you're right. There's so many platforms available. It would it seems like a, you know, an opportunity that's begging to be exploited.
well, you know, and our one thought is to see, I don't know if this will happen, but I have a dream that we have, you know, 1 out of 20 turbines is a tower, you know, so they're not, so we actually have really good measurements from fixed platforms and ultimately from floating platforms. If they can float a turbine, they can float a tower, making these measurements that we need. So
oddly, the wind farms will tend to have a METS tower within their configuration as well. And so the platform with, you know, and many of the instruments are already there. That's the tantalizing thing about it.
Who would pay for this? Like if we would like to have one tower in every 20.
well, you know,
where does the funding comes from?
Yeah, it might be part of the lease agreement. I mean, they spend a lot of money on getting leases for these areas offshore. So there's that. There's also, you know, I tend to think of DOE as having more money than most of our federal agencies, and this is you know, the sort of work you'd hope they'd support. So I think right now we're just too soon off our shores. The Europeans are way ahead of us, and actually most of the companies that come to our shores are European companies. But I don't know. It's just there are conversations going on about this, and you never know. So
Thanks, Jim.
Can you hear me now?
Yes, we can.
Loud and clear.
Yeah, it's Chris Farrell in Boulder. I like Jamie's arguments about needing fluxes and skin temperature. I wanted to make an additional point that just the skin temperature is not sufficient. You need the sea snake or some near surface bulk ocean temperature so you can get the actual cool skin part, which is, I think, as I recall, the effects on CO2 are sort of depend on computations of chemistry and solubility through the whole layer.
Yes, yeah, you're totally right. So we need bulk measurements at some depth below that's well calibrated and stable, as well as the skin measurement, ideally. Yes.
I agree, Chris. And my dream is to add a sea snake to these RCRV vessels that could be routinely deployed by the research techs under conditions of transiting. Yes, that's absolutely what we need. It's interesting. It's actually now easier to make the skin temperature measurements than it is to routine sea snake measurements, which you would think would be the simplest.
Yeah, that's why we want the skin temperature measurement, because the sea snakes aren't really practical for unattended use, and transit is the worst time to use them because they're snatching in and out of the water and getting torn up. And so we don't trust the data if the ship's underway usually.
Yes,
Well,
I can.
yeah, that's
sorry.
an interesting point. No, go ahead. No, we could talk about that later, I guess. But yeah, I agree that we need it's the bulk skin temperature difference that's modeled, not just the skin temperature.
Yes.
I think Jim Edson has another hands up.
oh, there we go. I guess I can unmute myself now. Yeah, I don't have much to add. I think I'm preaching to the choir. We did have a setup on the Sekuliak where we dragged a sea snake, and yeah, and we had really good agreement with the measurement in the sea locker they have on board, but that was under Gulf of Alaska conditions. So I don't know if you can extrapolate that into other conditions too. So it was pretty near neutral, for example, and so things worked pretty well there.
I think there was also some hands up from William Foran. I think now you could unmute yourself.
I think you should be able to hear me now.
Yes, we are.
Hi. Andy, earlier when Megan asked the question involving your optimal band pyrometer, you mentioned or replied with the intention to retrofit sail drones with the optimal band thermometers. Did I hear that correctly?
Well, I'm just saying if we that would be my recommendation to sail drone. If they want to get a good skin temperature measurement, they should switch to an optimal band and implement that, because I don't think they're going to want to add sky measurements to all of those for the issues of cost and also, more importantly, an additional draw on the power. Maybe, Bud, you should introduce yourself as you're representing Hytronics.
I put it in the chat, but yeah, sure. I'm Bud Foran. I work for Hytronics Infrared and have quite a number of years in support of infrared radiometers for a host of applications, including SST and other atmospheric measurement applications. And I'm located in New Jersey, in the US. So Andy, the unicorn appears to have a tube length longer than the tube that the present radiometer views through on the boom of the sail drone. And if your recommendation to sail drone will be to utilize the optimal band and choose the same location, I'd like to suggest that you suggest that the length of the tube be increased to help further recess the lens from the environment, because as we all know, a dirty lens is the #1 culprit of an apparent drift of calibration or source of error. Mm-hmm. So I just wanted to put that out to you and the group. And the for the FOV, the field of view that the current radiometers on sail drone measures, do you believe it could be okay to increase the field of view by some number of degrees? Because I have an idea that has been created while listening to the presentation today with regards to a chance to improve the NETD temperature resolution of the optimal band pyrometer, and it may require a wider field of view.
Yeah, I think that's something to consider. Just to clarify that I think that the unicorn or a configuration on the sail drone was a one-off. They're never going to do that again. Mm-hmm. So we need to plan on using the measurements from the boom. I'm not sure if that was clear there. So yeah, I think some of those things would be useful to consider.
Yeah, on the boom, but with a longer tube. And thank you for the reply on the chance for increasing the field of view. It's given me a really good idea, and I'll work on it with the factory. And then to Peter, you mentioned the differences in spectral sensitivity between the CT09 with 9.6 to 11.5 and the other model, CT15, KD15, and KT19, all have the same, but they're different from the CT09. And I just wanted to share that I got feedback 3-4 weeks ago that the factory is looking into modifying the CT09 spectral sensitivity so it agrees with the others. It's too early to count on it at this point, but it is something that is being looked into.
Good, thanks, Bert. I'm pleased to hear that.
Yeah, and also with regards to your comment about within a set of 4 CT15s, all having our defined 9.6 to 11.5 micron spectral range, and 3 of the 4 being of one batch and one of another, you are correct in that batches of filters are what is being referenced, or the issue here. And we do characterize the spectral sensitivity of a sampling for each batch that we receive, but we do not characterize the sensitivity of each and every single filter. And the emphasis that you placed on it with regards to the importance and the impact that it has on readings could lead me to make a request to the factory that when the importance is as high as you've described today, that we do in fact handpick and check each filter that goes into each instrument.
Right. I'm nodding there because I agree. Way back when my hair was not white and my beard was black, I worked on the development of the first ATSR that flew on ERS-1. And that was built in the UK. And we had the detectors made by a company, and we selected the filters. Yes, not the detectors, the filters, according to which agreed best with what we wanted.
Yep.
And they came in batches, and we did the spectral response function measurements for the filters and selected those for the flight models, which were most similar. I won't say identical, they were most similar.
Mhm.
Thank
Okay.
you. This is really a great discussion. But I would like to move on. I think there are other hands and other questions around. So maybe Yuangshu, if you want to continue, you can now
Yeah. Thank
unmute.
you,
Yeah,
Lucia.
thank you.
So I would like to come back to the conversation between Jim and Jimmy about like using this tower-based eddy covariance system to, to test if the Cook-Skin effect really influences CO2 flux. But I mean, I can get the point, like, because based on the tower, you don't need to do the motion correction. It's like reduce loss of uncertainty. But the question is like based on the tower, that I assume the tower will be on the coastal side. In this case, the CO2 will be influenced by the land. So the horizontal transport will influence loss of the fluctuation of the carbon dioxide mixing ratio. So I don't think this is it's a very good idea. And also another point is like if you really want to do this test, we need to compare the bulk flux with eddy covariant flux, right? And then which K would like to use, which gas transfer velocity would like to use in the coastal side. As we all know, the case maybe is different in the coastal side with the open ocean, right? So my idea will still be like using the shape in the open ocean with not very storm condition, maybe it's calm condition, wind speed not very high, and also the Cook-Skin will be higher, the influence will be higher, and at the open ocean, the K should be, better being constrained than the coastal side. This is one point. I mean, Jim and Jimmy, you can comment on that if you want.
Yeah, absolutely.
yeah.
I agree, Jianshu, that you're right. If you go to the open ocean, then K is more constrained, and so it becomes you're more likely to pull out the signal you want. So yeah.
Yeah, they like, I don't know if you can hear me, but like anything, there's trade-offs, right? Because on a ship, you have increased flow distortion, a lot more uncertainty due to that. You do have to do the motion correction. Ship at least you can, there's enough power to do things like drying the sample before you sample it. But depending on your coastal site, the Martha's Vineyard site has pretty open ocean look when you look at any wind direction from the south, for example. And sometimes you get more signal in those regions, which is maybe what you're looking for. So I think it's just a really good discussion that we should have. But I definitely have some reservations having tried to do this on making these measurements from a ship. So
I agree with that. I have another question maybe for Andy. So when we talk about the Cook-Skin effect, the delta T is calculated by the difference between the skin temperature and the bulk temperature, right? So my question is like, what's the definition of the bulk temperature? At which depths we should be used for this bulk temperature? As we all know, the diurnal warming will influence the temperature from the surface to maybe 5 meters is different. So which bulk temperature should be used for the Cook-Skin effect calculation?
Yeah, that's a challenge because it's actually harder. It's also hard to make that subskin temperature measurement if your boundary layer is only a millimeter or less. You really physically can't make that measurement. So what is done in practice from ships is use this sea snake, which is a thermistor that gets dragged in the wake of the ship. And so various hand waving arguments can say that measurement is within 5 to 10 centimeters, sort of a mixing of the near surface, and that's used as a reference from a practical point of view. We have done some measurements to compare with the sea snake using infrared imagery, where an infrared imager can show you the difference between basically the skin temperature and the bulk, and those measurements are consistent with that notion that you're measuring something within the first few centimeters. That's about from a practical point of view, I think what you can do, unless you have a profiler, which is very specific.
Okay, so did you see some difference of the Cook-Skin effect during the daytime and the nighttime?
Again, that's really going to be driven by how well you can measure your bulk temperature. So if you want to eliminate any diurnal warming effects, then you can just look at it during night. And we have basically, if you filter the data by the depth, we've shown that the skin temperature measurement, the sea snake measurement gets you as close as you can to the bulk temperature to eliminate that diurnal warming.
Okay, thank you.
Thank you, everyone, for the great questions. We have 5 minutes left, so I think there are a few questions that are still not answered in the chat, and I'm sorry, I don't know.
Okay,
Megan,
you had some questions and had your hand up. Did you want to come back or?
Oh, yeah, well, I did have a question in the chat about whether a user could add on the sensor, but maybe that could just be added in. Somebody can answer that in the chat.
Well, I could briefly address that. I think Saildrone is, as you deal with Saildrone probably more than anybody, but my sense is that they're not interested in adding anything custom that's not going to be used by a lot of people. So they were very helpful to add these sensors during this S mode for a demonstration. But I think I'm converging on the notion that if you use this optimal band, then you don't have to correct for the sky because you can estimate the radiance. I think that's from a practical point of view going to be the way to get good measurements from the Saildrone.
But that's a new sensor. That's a different.
Well, they could retrofit their sensors. Basically, it's just putting a different filter in the radiometer that they have, and that's what I've done with mine.
I get it.
So it's a cost of $1,000 per Saildrone, probably.
Okay, they need to do that. So maybe
I need to circle back with them, maybe with your help, to try to summarize these things for them and see what they can do going forward.
Right.
Andy,
So,
excuse me, Megan and Andy, I have to jump in. We cannot assume that the cost is as inexpensive as Andy just expressed. So
okay, sorry.
Yeah.
I would like to wrap up very quickly with if each of you of the panelists can just say something, like one idea of, as a community, what do we need to do, or even us as within the community of OASIS, what can we do to move forward to have more reliable and more widely available skin temperature. Just in one sentence, we have 3 minutes. I think that would be a great way to wrap up the session.
Okay, well, I'll lead off, and I'm really excited that, after 20, 30 years thinking about the skin temperature, that it's come back around. Its importance is being recognized. And I also think the international collaborations are really a great potential going forward to combine the gas transfer community and the skin temperature community.
Sandra, any thoughts?
Okay, so no, I'm not an instrument person, but I second Andy that it's a very good thing that this community is bringing up the cool skin effect, because as I said, we've been using these very simplified parametrizations forever, and maybe we're at a point that we can dig back the old models and try to include heat fluxes directly. So just calling attention to the cool skin is it's a pretty good thing. So yeah, thanks for that.
Yeah, Peter.
I have 2 points. One is, don't discount commercial ships. We have had a very good and continue to have a very good collaboration with Royal Caribbean Cruise Lines, and they have lots of our instruments on their ships, and we have generated very, very valuable data sets. So that's something. The other thing, I wouldn't dismiss mounting eddy correlation and skin temperature radiometers on the end of long piers. You can do conditional sampling so that you only take measurements, or you only analyze measurements when you've got onshore winds. And there's a pier off Australia, which I think is 1 kilometer long. And we looked into putting instruments on the end of that, but then the person we were dealing with moved jobs and went back to Europe. So 2 things there. I could carry on
Great.
as well, but I will.
Thank you. We have 1 minute, Jamie.
So I think there's a golden opportunity here. There's a clear need for digital reference measurements, and as Andy was saying, is an opportunity for the sea surface temperature community and the gas flux community to work together and produce something which is far more powerful than the individual parts themselves.
Good point.
Great. Megan, what?
I want to thank you, Lucia. You've pulled this together, and you really made this an important, roadmap for going forward for OASIS, and raised the skin temperature as being one of the highest priorities to address as a community, and bringing the carbon community and the physics communities together. So thank you so much for doing this. And I hope that going forward, we can bring more people in to help Lucia, and especially early career. Lucia is a early career scientist in Norway, a postdoc, and it would be really great to have others, helping her push everyone, the community, forward.
I'm looking at Zhuang Shu, even if his camera is off.
Thank you. I'm honored to be invited for that.
We really need to wrap up, otherwise they will get angry at me. But thank you everyone for joining, and I hope we can continue with this discussion, and I hope to be in touch with you. And sorry if there were a few questions that were not answered. Hopefully you know now who to ask. So please send emails to the people. So thank you everyone.
Okay, and thank you, Lucia, especially for organizing. It's been really great.
Thank you. Thanks, Andy, for all the help.
Okay.
Yeah.
Okay. Bye-bye.